You need to ask questions or I can't digress, okay? I've heard these lectures before. So the schedule will be, I'm lecturing today, Dr. Belmar will be tomorrow, I'll be in Dallas, and then I'm going to do 3 days next week. He'll be here on Thursday, that's the day he could do it. I think he may be a fair amount in the next week, but he hasn't given me his schedule because he's been out of town. But we'll try to keep this posted for you. But just to let you know, I think this brings me up to 75% of the way done by the end of next week for me, and he's going to be at least 50% done. So by the end of next week. So it moves along fairly quickly when you meet every day, and so far as that goes. But you'll appreciate it in May when you don't have a course, right, that you have to worry about. Last time we talked about their physical limits to materials properties, basically based on the bond strength of the atoms. I talked about mechanical strength, but it also melting temperature, and the highest bond strengths we have are about 3 electron volts per atom, which I can't remember, that's around 250,000 joules per mole or something like that. You can work out electron volts per atom to joules per mole. All you have to do is multiply by Avogadro's number, and convert from electron volts to joules. But in any case, there are limits to the properties of materials, and the Ashby plots kind of show you that. And he usually goes 5 or 6 orders of magnitude one way by 5 or 6 orders of magnitude the other way, and all materials sort of fall in those ranges. And if you want to be a material scientist, we can explain why. Okay, we can explain why many of the ceramics or ionic and covalently bonded materials are transparent. They don't have free electrons. No metals are transparent, except for the one transparent metal we know of. There's no Star Wars fans here, or Star Trek fans. Transparent aluminum, that's what they held the whales in the voyage home. You don't remember Scotty deciding to use transparent aluminum? Okay. Anyway, so go watch the voyage home. They had to save the whales or something anyway. Anyway, so metals have free electrons, and that's why they don't transmit light. They actually absorb light with all those free electrons. Anyway, so there are limits to the properties of materials. And then Mark Twain once said, rumors of my death are greatly exaggerated, but in fact he was speaking on behalf of metals when he said that. Most people don't know that he was talking on behalf of metals. But in fact, metals are here to stay. I showed you Ashby's plot where he predicted the demise of metals because composites and ceramics were going to take over the world, okay? And plastics, okay? Well, that hasn't happened. And believe me, we're going to talk in this course about why it's not going to happen based on the limits to the properties of the materials. Okay, and we haven't talked about this, but this is what we're going to go into today. Stone, cement, and steel are the only members of the billion-ton per year club. I guess I could show you that right now. Well, I won't show it to you right now. I'll show it to you in a little bit. We'll get to that today. If we look at something like strength, which is what we're interested in structural materials, versus relative cost, and remember, aside from externalities, which is kind of becoming the number one reason for selection of materials in many cases, we've always had availability and cost as two of the issues. And so this is Ashby's plot on cost. Again, 5 orders of magnitude. If you plot it on, and so you have to plot it on a log-log scale. But low cost is down this side, brick, stone, concrete, and here's mild steel. And it turns out there is a relationship between the amount of material we use and the cost. Duh. Okay. And here are your steel, brick, and stone, and concrete are the billion ton per year club, and nothing else comes really very close. Okay. All the plastics we'll see are about 300 million tons per year. Okay. And so the plastics are in here. And they're more expensive, so we use less of them. The ceramics, the fine ceramics have tremendous strength. If we plot something else, they're going to be way down at the bottom. What's that other thing we plot? This is the fracture strength. Ceramics have lousy fracture energy, okay, which is, so I don't have, that's the wrong plot. Fracture energy is the same as toughness. And I'll show you the toughness later, okay? So it turns out some of these other things, I mean, ceramics can be fairly inexpensive, but they have lousy toughness, and so therefore we have to be careful how we use them, although stone and concrete are ceramics. So there's exceptions to every rule, I guess. Now, there'll be a handout, and this comes out of Ashby's book. On his chapter 2 is the price and availability of materials. And if you look, he's got a plot in there of the availability, abundance of the elements in weight percent in the Earth's crust. Okay, actually atmosphere, oceans, and crust. Oxygen is the most abundant, silicon is the second most abundant, aluminum, iron, calcium, and magnesium. And it turns out I'm going to show you that these actually are in those billion-ton per year category. And if you look at the oceans, obviously you have a hydrogen and oxygen, and this is weight percent. And it turns out virtually everything is in the ocean. Okay, there's a certain solubility in water for everything. You can mine uranium from the ocean. You can take gold out of the ocean. A little pricey, okay, to extract it because it's fairly dilute, but the oceans are fairly large, and there's a tremendous amount of most things in the ocean if you want to pay the price. And of course, we generally know what's in the atmosphere. They never tell you what the 5% component in the atmosphere is. Anybody know what the 5% component gas in the atmosphere is? It's called water. We have rain, clouds, snow. And typically you start looking at, well, if you start looking at humidity tables and temperature versus humidity, you'll find down here near the Earth's surface, there's about 5% humidity, or 5% water in the air. At like 82 degrees Fahrenheit, 100% humidity is 5% water. Now, we don't have 100% humidity, but in any case, there's a lot of water up there. I once wondered, I don't know if you've ever wondered things like this, I see these storms come across the country, they're dumping all this rain, I thought, how much water is up there? And if you start calculating what the thickness of the atmosphere is, well, the thickness of the atmosphere that has clouds is, anybody have an idea? Now, if you were a Howard Hughes fan, you would know this. Howard Hughes developed pressurized airplanes so they could fly above the clouds so that you wouldn't have to worry about the weather. You can fly through the clouds and get above the clouds, but you get to high enough altitudes that you have to have a pressurized aircraft. So one of the things that made Howard, you didn't watch the movie about Howard Hughes? Actually, I'm not sure that's where I got this, but it's true. It turns out he essentially was one of the first people to decide to try to build a pressurized aircraft. Before that, the little biplanes and stuff, they'd go up a few thousand feet, 5,000 feet or something, and when they had bad weather, you couldn't fly. But by going up to 10 or 15,000 feet, you can get above the clouds. Now there are clouds that go even higher. Some of the clouds go to 40,000 feet, but if you just take 10,000 feet of space that might have, and the humidity is not 5%, it may only be 1% moisture in the air, and you start thinking about 1% times 10,000 feet, that's a lot of rain, okay? You can dump feet of water. You know, those clouds still got plenty of moisture when they come from the Pacific all the way to the Atlantic. So anyway, here's the relative abundance, and there's other numbers for abundance. It turns out, if you look, a geologist would look at, well, the geologist did the other plot too, but if you look at the abundance in terms of kind of marching across the atomic number, the periodic table, if you will, of course, we have a lot of hydrogen, in relative abundance, but it decreases as we get to a larger and larger atomic number. Does anyone know where the elements were formed? In the Big Bang, at the time of the Big Bang, the elements didn't exist. Where are the heavy elements formed? They're not formed in the sun, right? Pardon me? No, not the core of the Earth. They are in the core of the Earth, but it turns out when you have a supernova explosion, it's such an energetic event that that's where nature basically has its atomic reactor where it has enough energy and things are slamming together so hard that you actually take light elements and make them into heavy elements. Now we can do that at billions of dollars per gram in some reactor here on Earth, but in the heavens it's basically done in the supernova. It turns out, if you look here, iron has this sort of interesting peak above and other things around it. Iron and nickel are very high abundance. Meteorites are typically iron and nickel, high in iron and nickel. Does anyone know why this is? Any nuclear engineers in here? It's because if you look at the stability of the atomic nucleus, it turns out atomic number 56 is the sweet spot for the nuclei. Very, very stable nucleus. You don't have a lot of problem with radioactivity in iron compounds and stuff. The nucleus is very stable. And as a result, when these supernovae occur, you produce a lot of iron and nickel. This basically is the productivity curve for supernova in producing heavy elements. We don't produce them on Earth. We don't produce them in big stars. We only produce them in big stars when they blow up. Okay? Now, I talked about the fact that there was a lot of oxygen in the crust. Most of the metals, or most of the elements in the periodic table, are present as either oxides or sulfides because that's more thermodynamically stable. And as a result, one of the problems with metals, which I think metals are wonderful because I'm a metallurgist, but metals have a very high price to pay to get them into the metallic state. They tend to exist in an oxide or sulfide state. Aluminum oxide is known as bauxite. The ore is called bauxite. It's mostly Al2 oxygen plus OH, okay? It's got some water and stuff in it. But basically, it's very, very stable. The free energy of formation of aluminum oxide is very, very high, and it takes about 300 gigajoules per ton to produce aluminum. Plastics, on the other hand, are about 100 gigajoules per ton, and most of that is the energy content of the plastics. Essentially, you could have been using that plastic and you could have turned it into a fuel to burn in your airplane or your car, and a lot of that is I guess you can avoidance of being able to use it as a fuel unless you're recycling it. We can recycle plastics fairly readily by just burning them up because they are a fuel. Copper is very high and it's going even higher. Does anyone know why? Something called entropy, okay? Copper ores are not very concentrated. In fact, anyone know the largest copper mine in the world? Or actually the deepest one in the world? You fly over it sometimes as you go out of Salt Lake City Airport. It's about 2.5 miles deep, okay? It's the Bingham City mine or something like that, or Bingham Canyon or something, I can't remember. But Kennecott Copper owns it. It's been mined for 100 years. They just kind of keep digging it deeper and deeper. The ore there is less than 1% copper. Okay, it's about, I think it's like 0.5% copper. There were ores in the Belgian Congo, which is now Zaire, but it was the Belgian Congo in the 1950s, and there were ores that were 6% copper. We just depleted all those rich copper ore reserves. And so copper takes lots of energy, and we do essentially mine for copper. We can get a bauxite that's very, very rich. We can get iron that's essentially pure iron oxide. Copper is dispersed at very low concentrations, and therefore you got to overcome a lot of entropy to get it. Zinc is usually, now zinc is usually a byproduct of other things. Steel, there's iron ore all over the world because steel is one of the most abundant elements. Glass, cement, and things. Anyway, there's a list here, you'll have it, of the energy content. And as a result, people like to think, oh, aluminum will overtake steel. No, not in price, okay? Yeah.
So is there any correlation or any significance of how much energy it takes to convert aluminum? Does that mean it's stronger or better, or is it just like here's a fact? Or it's just a fact?
Well, it depends on what property you're talking about. Corrosion resistance, I mean, things that take a lot of energy often give up, well, they will give up a lot of energy to go back to their oxide state. And so sometimes they have corrosion problems. Now, it turns out not to be true in aluminum because it forms a nice protective oxide skin. It tends not to be true in titanium. It turns out the Achilles heel of iron, of steel, is corrosion. And steel's got, 50 on this scale, okay, whatever the scale is. Does this thing quit working? Yeah, it quits working every now and then. Okay. So there's other factors, okay? The only factor I can draw a correlation to is price, because energy is the price, okay? But there are other correlations. I mean, the Achilles heel of metals compared to ceramics and polymers and plastics is they corrode. Plastics, you throw your plastic baggies away and they'll be floating around in the ocean for the next millennia, okay, or longer, because bugs don't even eat them very well. Throw metal in the ocean, unless it's a very corrosion-resistant metal, it's gonna corrode in that environment. You throw cement in the ocean, and it'll be there probably a million years from now. Well, actually, not a million years, but in fact, the cement originally came from the ocean. It was formed as limestone in the ocean as a deposit. It precipitated out of the ocean. That's another story. So you actually have to get into the details. I guess I don't have a simple answer to your question, okay? Other than there's a price correlation because energy and price are basically fungible. Okay? Then there's a handout that is the summary of this course, okay? And I don't know if we've mentioned this in this class, but anyway, this is a handout that I was on a committee once in early 2000. I think this is, I don't remember what it's like a 2002 or 2003 copyright. This is a National Academy of Sciences report, or National Research Council report of the National Academies, on materials research needs for the Defense Department in the 21st century. So there were about 40 of us on this committee, and people were talking about all these fancy new materials and how they were going to do all these wonderful things. And does anybody know how the National Research Council works, or the National Academies works, or anything about those things? Okay, so Abraham Lincoln chartered the National Academies of Sciences in 1863. And there were about 8 or 10 people at this thing, and many of them were politicians, but somewhat scientists or whatever at the time. And the National Academies is not part of the government, but they have a charter from the federal government. And their charter is to advise the government as a sometimes they're called a quasi-governmental agency, whatever that means. But their job is to advise the government on matters of science and technology, and now medicine. And so the National Academies went plodding along until about the 1950s or 1960s, and then in the mid-60s they formed the National Academy of Engineering. A few years later they formed the Institute of Medicine. And so the National Academy of Sciences, first of all, you have to be nominated by people who are already in the club. Okay, as Professor Sekeli, who's passed away, used to say, it's more important to not be in the academy than to be in the academy. I mean, once you're elected to the academy, You really don't have to do anything, although you'll be asked to serve on committees. But even if you're not in the academy, you'll be asked to serve on some of these committees. And some people serve on these committees because they hope that this will help them get elected to the National Academy. Okay, so the other thing about the National Academy, it's literally an old boys club. And by that I mean there's less than 5% women. Okay? Now they're trying to change that. They actually have quotas. So if you actually happen to be a fairly highly qualified woman, there's a very good chance of being elected to the National Academies. They also have quotas against academics, because it turns out the National Academies are about 40%, 45% academics, and they have a quota. They don't want to be more than 30% academics. So to be a white male at a university, the chances of getting elected to the National Academy are near, I mean, they're not, they still, it's an old boys club and it still elect a lot of old boys. In fact, talking about old boys, I think one year the average age of election was like 73, okay? Because they have a limitation. They just announced who got elected like a week ago. It's usually in February for the National Academy of Engineers. And they elected 80 people, okay? There's a total of about, in the 22 foreign associates, there's only about 2,000 members of the National Academy of Engineering in the country. And there's about 2 million engineers, so you're in top 1 out of 1,000, sort of, whatever that means. But as Professor Kelly says, it's more important. A lot of people are very, very envious. For example, I actually was elected when I was department head at age 47. Not the youngest, but I'm one of the younger people to get elected to the National Academy. And when I stepped down as department head, Professor Suresh, who's now president of Carnegie Mellon and became Dean of Engineering here and was a candidate for president of MIT, Professor Suresh would take me to lunch about once every 3 months for the first year and a half or 2 years after I stepped down as department head. And at the end of the lunch, the National Academy always came up because he was not a member yet, okay? And he knew that to a certain extent, he was afraid that I might blackball him or something. Well, I'm not that type of person to blackball somebody. But it was interesting. When the people have been nominated, when the thing comes out for the first comment, which is in the summer, he kept the schedule. This is all supposed to be very secret for the nominations and the elections, okay? But he knew it all the time, what was going on. And he took me to lunch in that July or August of 2002 or 2003, whatever it was. And that because he knew he had been nominated. He had been nominated by my predecessor as the department head. And you have to be nominated by 4 or 5 people. And you can't have everybody from the same institution. I mean, there's a lot of politics to this stuff, a lot of politics. Anyway, and so he took me to lunch, and the National Academy came up just like it did every time. And once he knew that this comment stage, I never got another lunch. He was department head for another 5 years, but I never got another lunch. Okay? But, I mean, I got free lunches for every quarter for about a year and a half. It was a waste of time, but anyway. Anyway, so the National Academies also have the National Research Council, which has been around since around 1910 or so. And they do studies for the government. Congress might commission a study, or the Defense Department, some undersecretary of defense wanted to know, what are we going to spend our money on in the future? And rather than listening to their own scientists, for example, the U.S. Army, about 5 years before this, had spent over $1 million trying to study what was the material that the U.S. Army was going to purchase the most of over the next 20 or 30 years. And they came up with a study that I could have told them, and I wouldn't have taken $10 million to study it. You know what it was? It is steel. Why? Well, you don't throw stones at the enemy, okay? You kind of shoot missiles and things, or you bring a big tank in and stuff. And there's a reason why we use steel, and we'll talk about all that. But anyway, so I was on this committee, and they were talking about all kinds of fancy new materials and glamorous technology materials. And they asked us all to write up our stuff, and they have editors down there that will put it together in a big report. And these reports go to Washington, they're in Washington. They go to the Capitol Hill, and the congressional staffers read these things, and they'll influence the funding and things like that. So it's worth spending some time on these things, plus you meet a lot of people. This is the Division of Engineering and Physical Sciences. So anyway, I wrote up my stuff, and I basically wrote up what I've been teaching my class, okay, in 3 or 4 pages. And it basically said the old traditional materials are important. Well, this is not what they wanted to hear, and it didn't fit into anyone else's talk. So this became an appendix, okay? Doesn't have my name on it, but I'm the only person who contributed to it. Okay, so, but this is a summary of what I've been teaching. And they called it Integration of Material Systems and Structures Development. But it's not that it's all of my stuff. In fact, it's stuff I've been learning from other people from time to time. But here's a plot from Jack Westbrook. Jack Westbrook is a graduate of this department. He put this together. He's retired. At that time, he was retired from General Electric. I gave a reference because they wanted it. I guess I had emailed Jack. And he was already retired then, but he put this together in 1962. So these are $1962. It was an internal memo at General Electric. And it shows structural materials, dollars per pound versus pounds per year that were used. And here's stone. Well, I guess I can blow it up for you a little bit. So here's stone up here, the most highly used material in the world. And it has been for millennia, okay? Here's cement, here's carbon steel. He's got alloy steel down here, used at about 1/10 the volume, okay? These are large numbers, 10 to the 11th pounds per year. That's a lot of material. These are ISO market size, okay? This was a $1 billion market in 1962. It's probably a $100 billion market today. But in any case, and you come out here to the end, well, diamond is a structural material. You may not build buildings out of it, but it's a structural material. You're using it for its mechanical properties, or its optical properties. Well, I don't have a diamond, but people use it for optical properties. But as a structural material, it has important uses. And remember, this was a General Electric report, and at the time, General Electric had a near monopoly on man-made diamonds because of Tracy Hall, among other people, okay, who had invented the process to make man-made diamonds. Okay, cemented carbides are structural materials just like diamond, not used, at $100 a pound. Diamond is, back then, was $10,000 a pound. It's about $400 million a pound now, or something like that. Ashby's got some updated prices and stuff. But anyway, you could read this, but there's also something in here, and I've already told you this other thing that's in here, and that's the value of a pound saved. And the value of a pound saved of the life of a vehicle is 20 cents a pound for ships and railroads. Anybody remember what it is for automobiles? $2 a pound. And aircraft, 200. And spacecraft, 20,000. So I've already used those numbers a number of times. And you can sit here and debate. Some of these numbers have changed by a factor of 2, and we will talk about some of these things. $200 a pound. I remember the first LFM thesis, the LGO thesis, the first round of students, one of them went to Boeing, and they actually got the proprietary Boeing number for the value of a pound saved on an aircraft. This was sort of proprietary, but they somehow got permission, or maybe they didn't get permission. It showed up in their thesis. $188 a pound was Boeing's number. Pretty close to 200, right?
It all depends on the cost of fuel, right?
Yes, exactly. I used to use $2 a pound for automobiles 20 years ago, 25 years ago. And that was when fuel cost. In fact, if you read this article, it was early 2000s. I talked about fuel at $1.50 a gallon. Well, we haven't seen that for a while. We might see it again, but And I gave a talk once about, in fact, I think I reference in here Peter Breidenbaugh, okay? Yeah, I do, okay? So Peter Breidenbaugh, Private Communication, October 11th, 2001. So I went to a conference, okay, and there was Peter, graduate of this department, Senior Executive Vice President Alcoa. He was in charge of all the stuff to make all aluminum Audis with Audi, okay? And that was all under him. And we were both in the same session, and I got up and gave a talk sort of about this type of stuff. And I said, I knew he was in the audience, so I said, you know, all aluminum vehicles automobiles will not really be economical until gas costs about $4 a pound. Because I knew I didn't want to offend him, okay? I was sort of upping it. I'd used $2 for years in the 1990s, but this was the early 2000s and stuff. Peter came up to me at the break. He says, "No, Tom, it's $2 a pound." He was using the same number I was, okay? Because that's what the real number was back then. But it does depend on what the price of fuel is. And it could go up to $4, but it's not 200, and it's not 20 cents a pound. But you're absolutely right. When you have fuel that's varying by a factor of 2, then this number has to vary by a factor of 2, because it's based on the price of fuel for automobiles. It's based on the price of fuel and drag in the water or on the railroad tracks, the friction on the railroad tracks or the drag in the water and the price of fuel for ships. And here, for aircraft, it's based on the price of fuel, but per 100,000 hours for a commercial aircraft. And for spacecraft, it's just, again, it's sort of the fuel to get a pound in orbit. And you go look at the numbers, back when we were shooting rockets off in the Apollo program, it was costing $5,000 to $10,000 a pound in the 1960s to get a pound in orbit, a pound of payload in orbit. And the purpose, if you go back and read the 1970s documents, the purpose of the space shuttle was to drop the price from $10,000 a pound to $1,000 a pound. And anybody know what I think I said it in here. Anybody know if you look at the actual space shuttle and its history of 30 years of use, what its actual cost of a pound of payload in orbit? Remember, it's supposed to drop the price by a factor of 10. That's what they told Congress when they asked for the program to build a space shuttle. Yeah, it was about 30,000. I've heard 30,000. It could have been 40,000. But because of the Challenger, you know, the disasters and the efficient management we have at NASA and all these other things, the program that was supposed to drop the price from $10,000 a pound to $1,000 a pound actually came in at $30,000 a pound, or $40,000. I don't know what it was exactly. I'm sure it depends on how you do your accounting, right? Yeah.
Do you have any idea for what it is for like an electric vehicle? If it's like a battery?
The answer is no, but now I'll speculate. Okay. First of all, the electric vehicle is using electrons. Those electrons actually have to come from somewhere. And if I look at the cost of a watt as either a fossil fuel watt or an electric watt, you know electric watts cost more, right? By about a factor of 50 to 100% more. That's just price of wall plug energy for electrons. So electric vehicles are much more efficient, but in their use of energy. But they're using a more expensive form of energy, namely electrons. And it all goes back to what was your source of energy. Hey, if you got solar energy and you can get solar energy down really, really cheap, but right now, solar energy is still costing you 20 cents a kilowatt hour if you're a regular consumer, right? So there's still problems here. And people don't always look at the whole system cost, okay? So in some ways, you can run the math and say electric vehicles are very efficient and cost effective, but if you look at the total cycle price, right now they're more expensive. Now, I'm rebuilding my house. In fact, if you went to my house right now, they just started digging out the basement. Okay, this is an 80-year-old home, and if you go up to the first floor or the second floor, you can see right through the house. They took all the walls off, all you see is studs. Okay. But as they're rebuilding it, I'm going to have 3 electrical outlets in my driveway. I don't have an electric vehicle now. And I couldn't buy an electric vehicle because I'd have to pay $1,000 or $2,000 to buy a plug to put in my driveway or my garage. Well, since I'm having the whole house rewired, because I've taken it down to the studs, okay, I'm putting in 3 of them, because I traditionally own 3 cars. 1 for my wife, 1 for myself, and 1 to go in the shop. Oh, that's my philosophy. When my kids were around, we had 3 cars, 1 to drive to high school. But now we're empty nesters. I have 1 so that we can go to the shop. Anyway, so you can read that article about the price and availability of materials. And I talk about things. Did you know how important are materials in terms of manufactured product? Not very. Did you know what the value of materials are in a manufactured product? The most materials intensive products that I know of are pipelines or big steel transmission towers to carry, 250 kilowatts of energy, right? Not kilowatts, but kilovolts. And those have about 30% of the cost of the project is the material cost. This is all in the thing, okay? So, it's just a slide I made from stuff that's in there. Automobile or an aircraft, typically it's about, materials cost are about 10%. If you're talking semiconductors and spacecraft, your materials costs are nothing, okay? Where's most of the cost of material? Where that paper will tell you that if you just kind of average materials costs as being about 10% of the value, then you're going to have another, well, actually I might as well read it. I just can't remember it. I had this all worked out once. Here's the table. Raw materials are 10 to 20% of the value of a product, manufactured product. Design and engineering is 10 to 20%, unless you're designing a hula hoop, which doesn't have a lot of design and engineering. Fabrication, forging, machining, and all that stuff, those things you mechanical engineers do, that's 20 to 40% of the manufactured cost. Non-destructive testing and quality control can be 10 to 20%. G&A, the accountants and the HR people and everything is 10%. And profit, if you add all this up with the ranges up above, is either plus 10% or minus 10%. You can either win or lose in this game, right? So, but those are the approximate numbers. And so, I'm not really popular with the other faculty in the materials department when I start putting up numbers like this. Because it says, gee, materials are only a small fraction of the manufactured cost. But I'm a manufacturing engineer, folks. I'm not really a material scientist. I'm certainly not a material scientist. I'm somewhat of a materials engineer. But anyway, you'll find some principles in there that I think they sort of go against the grain. And out of the 40 people on this National Research Council committee, well, maybe that's why they don't ask me to be on committees anymore. Okay, I tell them things they don't want to hear. Okay, so what can I do? I have a captive class of students, and so you guys have to hear it. But to give you an example, and I think I referenced that example in here, the U.S. Navy once was worried about the weight of aircraft carriers. Aircraft carriers gain 250 tons a year. I gain a little weight each year too, right? But if your spouse is giving you a hard time about, gaining weight, I don't gain as much as an aircraft carrier each year. Okay. But aircraft carriers, the Nimitz class started at like 60,000 tons or 65,000 tons, and it was up towards 90,000 tons 60 years later. And it turns out most of the weight is up at the top. For me, it's in the middle, but it's up at the top. It's only at the top if I'm lying down, I guess. Anyway, in any case, the aircraft carrier gains 250 tons a year, and they needed to make it lighter weight because it was going to cost them $50 million to design a new hull. And so around 2000, they gave a $1 million contract to Newport News Shipbuilding to do a feasibility study of what if they used a 65 KSI strength steel rather than a 36 KSI steel or 50 KSI steel, which was traditional in shipbuilding. What if they went to a higher strength steel? how much weight could they save and what would be the total savings. Well, at that time, a HSLA 65 steel would cost you about $1 a pound, $2,000 a ton for the plate. And they determined that they could save, it would cost them manufactured $10 a pound to fabricate the steel. I wish I still had the report. Anyway, lost it in my office somewhere. But that's 10%. The material cost was 10%. I could have done that for less than $1 million. I would have given them that report for $500,000, right? I mean, it's just a rule of thumb. And these rules of thumb are not bad. Now, if we look at structural materials usage, this is something I put together for this course a couple of years ago. It turns out, well, I gave you the future of metals thing the other day, yesterday, but steel right now is about 1.5 billion tons a year. And the next closest metal, remember I said steel was 95 tons out of every 100 tons of metal that was made in the world? The next closest one was aluminum at 1.75%. Turns out, here it is, 45 million tons of aluminum is what the Aluminum Association says the worldwide production of aluminum. Go down, the next largest is copper. That was 1.2% of the total. And you go down here, and I just picked off some others. I Googled scandium once, and worldwide production of scandium is 2,000 tons a year. Ta-da! What do you use scandium for? Anybody know? No one from an aluminum company? Baseball bats! Okay, it's an alloying element that the Soviets developed to give very high strength aluminum alloys. And the highest strength aluminum alloys go into baseball bats. Okay, that's another story. But I also estimated, okay, you can actually get, off Googling a little bit, you can get the total amount of cement or plastics. Plastics are 300 million tons, 20% of the volume, no, not 20% of the weight of steel. The volume's a lot larger because it's actually, because the density of plastics is a lot less. Actually, why don't we, no, I'll pass these around next time. We can talk about some other things. I always go slower than I think. But cement is 2.2 billion tons. And stone, this is just my estimate, because stone is used in, cement, okay, Portland cement. It's used in railroads, put it down as the foundation before they put the ties down and stuff. I mean, a lot of weight goes into all those railroads, okay? They, go look at the Stata Center over here. Not the Stata Center, but the new nanotechnology building. Go look in there. They're putting stone in the bottom of that. Crushed stone, okay? There's as much weight in stone there as there probably is in concrete right now. But stone's used for lots of things. It's not always a structural material, but it is a structural material. I've estimated there's probably 6 billion tons a year of stone, okay? It's the cheapest material, which is why we use a lot of it. There is this correlation between price and the amount of material that we use. Now, there are other relative cost and density. Ashby gives you some of these numbers. And what happened to my focus? Here is, and these things will be on the website so if you want. You don't have to copy them down. If I use iron as my metric for these metals and for both density, normalized to density and cost of iron, aluminum, which has 6 times the energy content, has 5 times the cost, okay, approximately. Well, you could argue maybe it has 6 times. But approximately, there's the ratio of the energy cost in the material, okay? And now it is much lighter, and that's what I was going to pass these around, but we'll pass around. This is a bar of aluminum, this is a bar of magnesium, this is a bar of zinc, which is about the same, some titanium, nickel and stuff. And you can feel the difference in density. Magnesium's really light, okay? Yeah.
Does that help understand, like, when you're thinking about this cost, like, what kind of metal you want to use?
Yeah. It turns out, I told you it's $200 a pound for an aircraft. That's for the whole aircraft. Or it's $2 a pound on an automobile. If I put the aluminum on the sprung weight on the wheels or on the brake pads, it's worth about $10 a pound. Okay? And I have a slide that I may put up sometime. The faster something goes, the more valuable saving weight is. And so all this density stuff turns out to be very important. And aluminum is a very important material. It's more expensive than steel, but it has a tremendous advantage over steel in several ways. If we go back to this stuff, the billion ton per year club, due to cost, I've already shown these guys are the lowest cost materials. That's why they're the billion ton per year club. Availability, well, you know, if platinum is a wonderful high temperature material, but the cost is not so great and the availability is not so great. Okay, and those two are related. Strength, we're going to talk about strength, but we have the Ashby plots, and strength can be all over the place. Portland cement's not that strong, but it's cheap enough that you can. Toughness, well, the metals win here. Okay, this is why metals are important, it's because of toughness. Portland cement's not very fracture resistant. Okay, steel is. Recyclability, okay, steel is like 80% recycled now. Aluminum's like 50% recycled. And they're trying to get aluminum up to 70 or 80%. What's concrete recycling now? Almost nothing. And it's 2.2 billion tons? You want to solve a world problem that's coming up? What are we going to do with 2.2 billion tons when it comes back after its useful life? We're going to have some pretty big landfills. Oh, actually, we'll fill in the ocean. We'll have a lot more dry land, right? Except all the water's going to rise. Never mind. High temperature capacity, corrosion resistance. I put this in parentheses because steel's Achilles heel is it corrodes. It wants to go back to iron oxide or iron sulfide. And it will, and it does. And it helps us to produce more and more steel each year to replace the junk. Hey, they just dug up my basement. I went home yesterday. They just dug it up. Cast iron pipes, sewer pipes. Good thing I dug up the basement. I was going to have to do it again sometime in the next 10 years because those pipes have been down there for 80 years. They're not much good. Okay? And I was discussing whether they should put in plastic because if I put plastic sewer pipe in, it'll be there 150 years from now, and I may not be alive by then. Okay? So every material has its own niche, and there are multiple niches, but these three materials are used in extremely large volumes because they have an interesting combination of niches. And remember, number one is the externalities, number two is price, number three is availability, and then there's all kinds of other things. And yesterday's conclusion is material selection is a multidimensional problem. Okay? And I was going to go through, I have grocery shopping in here, and we're going to talk next time about packaging materials. It can be plastic, can be paper, can be composites, can be aluminum, can be steel. I got some chili with beans in here, in a steel can. But they have to paint that can on the inside because otherwise it would corrode just like my sewer pipes. Even faster than every 80 years. Okay? So anyway, we'll finish a minute early, or 2 minutes early, unless anybody has a question. Okay? So Dr. Belmar will be here tomorrow. You can have Monday off. My treat. Okay? Tuesday I'll be back.